The universe is a place of endless wonder, filled with secrets that defy our understanding. Just when we think we've grasped the rules of reality, the cosmos throws another curveball, phenomena so bizarre, so inexplicable, that even the brightest minds are left scratching their heads. Imagine staring into the night sky, knowing that hidden among those twinkling lights are mysteries that challenge everything we thought we knew about space, time, and the very fabric of existence. From rogue planets drifting alone in the void to stars that vanish without a trace, the galaxy is brimming with puzzles waiting to be solved. And that's exactly what we're diving into today, 30 of the most mind-bending, awe-inspiring galactic phenomena that science can't fully explain. These aren't just curiosities, they're cosmic riddles that push the boundaries of human knowledge, forcing us to question what's possible. Some of these enigmas hint at forces we've yet to discover, while others seem to break the laws of physics as we know them. Think about that for a moment. In a universe governed by rules, there are still events so strange they make scientists pause, rethink, and sometimes even admit we just don't have the answers yet. What's even more thrilling is that these mysteries aren't tucked away in some distant corner of the cosmos. Many of them are happening right now, shaping the universe in ways we're only beginning to glimpse. Whether it's eerie radio signals from deep space or black holes behaving in ways they shouldn't, each one of these phenomena tells a story about how much we still have to learn. So if you've ever looked up at the stars and felt that tug of curiosity, that desire to uncover the unknown, you're in the right place. Buckle up, because we're about to embark on a journey through the most perplexing, breathtaking wonders the galaxy has to offer. And trust me, by the end, you'll never see the universe the same way again. One of the most tantalizing cosmic mysteries isn't something we can see, it's something we heard. Or at least we think we did. In the quiet pre-dawn hours of August 15, 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up a signal so powerful, so unusual, that the astronomer who discovered it scribbled, "Wow," in red ink right on the data printout. That single word gave the phenomenon its name, and decades later, it still stands as one of the most compelling and frustrating enigmas in the search for extraterrestrial intelligence. The wow signal lasted just 72 seconds, but in that fleeting moment, it blasted through the static of space with an intensity unlike anything astronomers had ever recorded. What made it so extraordinary? For starters, it was narrowly focused, appearing in only one of the telescope's two receivers, suggesting it came from a specific point in the sky near the constellation Sagittarius. Even more intriguing, it matched the exact frequency scientists had predicted an alien civilization might use if they were trying to communicate, 1420 MHz, a quiet spot on the radio spectrum where cosmic noise is minimal. It was as if someone had dialed Earth's number and hung up before we could answer. But here's where the mystery deepens. Despite countless efforts to find the signal again using more advanced equipment, scanning the same patch of sky, even waiting for the Earth to orbit back to the same position, it's never been repeated. Not once. Some theories suggest it might have been a natural phenomenon, like a comet reflecting radio waves, but no known cosmic object fits the bill. Others argue it could have been a glitch, but the signal's clarity and precision make that hard to swallow. And then, of course, there's the possibility that still sends shivers down spines. What if it really was a message, a cosmic hello we weren't meant to hear twice? The wow signal is more than just a scientific curiosity. It's a reminder of how vast and silent the universe really is. In a cosmos filled with trillions of stars, we've only managed to catch one fleeting whisper, one that refuses to speak again. Whether it was the work of an alien hand or some bizarre celestial fluke, it challenges us to keep listening, to stay curious, because out there in the darkness, something extraordinary might still be waiting to be heard. If the wow signal left us scratching our heads, dark matter is the cosmic shadow that's been tugging at the universe's sleeves for decades without ever showing its face. Picture this: every galaxy, every cluster of stars spinning through the void, behaves as if it's being held together by something invisible. Stars on the outer edges of galaxies rotate just as fast as those near the center, defying the laws of gravity as we know them. It's like watching a merry-go-round where the horses on the outside are whipping around just as quickly as the ones in the middle, even though no visible force is pushing them. That's the enigma of dark matter, an unseen substance that makes up 27% of the universe, outnumbering ordinary matter by a factor of 5 to 1. So how do we know it's there if we can't see it? The clues are written in the cosmos itself. Take galaxy clusters, for example. When astronomers observed how light bends around these massive structures, a phenomenon called gravitational lensing, they realized the distortion was far too extreme to be caused by the visible matter alone. It was as if an invisible hand was warping space-time itself. Then there's the cosmic microwave background, the faint afterglow of the Big Bang. Its intricate patterns reveal how matter clumped together in the early universe, and those clumps only make sense if something extra, something dark, was pulling everything into place. Yet for all its influence, dark matter remains maddeningly elusive. Scientists have designed exquisitely sensitive experiments to catch it, from detectors buried deep underground to satellites scanning the heavens for faint traces of its particles. Some theories suggest it could be weakly interacting massive particles that barely interact with normal matter except through gravity. Others propose actions, ultra-light particles streaming through space like an invisible river. But so far, every experiment has come up empty. Even the Large Hadron Collider, which famously uncovered the Higgs boson, hasn't spotted a single dark matter candidate. What makes this mystery so tantalizing is that dark matter isn't just a missing puzzle piece, it's the frame holding the entire picture together. Without it, galaxies would fly apart, the universe's structure would crumble, and our very existence might not be possible. And yet, after decades of searching, we're still left with more questions than answers. Is dark matter a single type of particle, or a whole family waiting to be discovered? Could it be evidence of extra dimensions or a shadow universe parallel to our own? The more we learn, the more we realize how much of the cosmos remains hidden in plain sight. Dark matter isn't just a scientific challenge. It's a humbling reminder that the universe still has secrets it's not ready to give up. Fast radio bursts are like the universe's most mysterious Morse code blink, and you'll miss it flashes of energy that erupt with the power of 500 million suns, only to vanish without a trace. First discovered in 2007, these bursts last just milliseconds, but in that sliver of time, they release as much energy as our sun does in decades. What's even stranger, most of them never repeat. One dazzling pulse, then silence, leaving astronomers scrambling to figure out what could possibly produce such a brief, violent signal across unimaginable cosmic distances. The first theories pointed to cataclysmic events colliding neutron stars, evaporating black holes, or even the explosive deaths of ancient, hypermagnetized stars called magnetars. But then, in 2016, something changed everything. A fast radio burst labeled FRB 121102 did the unthinkable. It repeated. Not just once, but over and over in unpredictable patterns. Suddenly, the idea of a one-time cosmic explosion didn't fit. If these bursts could recur, whatever was causing them had to survive the event itself, ruling out most destructive explanations. That's when the speculation really took off. Could these bursts be the result of cosmic lighthouses rapidly spinning neutron stars with magnetic fields so intense they twist spacetime itself, sending out beams of energy like a celestial strobe light? Some scientists think so. Others have proposed even wilder possibilities, like asteroid collisions with neutron stars or cosmic strings, hypothetical cracks in the fabric of the universe left over from the Big Bang. And yes, because it's space, the alien question inevitably comes up. Could these be accidental leaks from advanced civilizations powering interstellar light sails or even deliberate signals? While that idea grabs headlines, most researchers agree it's the least likely answer. But in a universe full of surprises, who's to say? What makes fast radio bursts so fascinating isn't just their mystery, but what they're teaching us about the cosmos. As these signals travel billions of light years, they pass through gas and dust, leaving faint fingerprints that let scientists map the universe's hidden structure. It's like using a lightning bolt to illuminate a dark forest. Suddenly, we can see the invisible. And with new telescopes coming online, like the Canadian Hydrogen Intensity Mapping Experiment and the Square Kilometre Array, we're on the verge of detecting thousands more bursts, each one a potential clue. For now, fast radio bursts remain cosmic riddles, reminding us that even the briefest flashes in the night sky can hold the keys to understanding the universe's grandest secrets. Whether they're the death cries of distant stars or something far stranger, one thing's certain: the universe has a flair for the dramatic, and we're just beginning to decode its greatest hits. Somewhere in the depths of space, an unseen force is pulling us and everything around us toward a cosmic rendezvous we can't even see. Meet the Great Attractor, a gravitational anomaly so powerful it's dragging our entire Milky Way, along with thousands of other galaxies, toward it at over 2 million kilometers per hour. The strangest part, we don't know what it is. This mystery lies in a particularly frustrating corner of the sky. The zone of avoidance, an area so thick with dust and stars from our own galaxy that it's like trying to peer through a cosmic fog. Imagine standing in a dense forest, knowing there's a roaring waterfall just beyond the trees, but no matter how hard you squint, the leaves keep blocking your view. That's the challenge astronomers face. The Great Attractor sits right behind the bulge of our Milky Way, where interstellar dust and starlight drown out almost everything behind it. But here's what we do know. In the 1970s, scientists noticed something odd. Galaxies in our local supercluster weren't just drifting randomly, they were all streaming toward the same invisible point. The sheer scale of this motion suggested something colossal, with the mass of tens of thousands of Milky Ways was yanking everything inward. At first, the leading theory was a massive cluster of galaxies, but when telescopes finally pierced through some of the dust, what they found was underwhelming. Just a modest collection of galaxies called the Norma cluster, nowhere near dense enough to explain the pull. So if it's not a single enormous structure, what could it be? Some researchers believe the Great Attractor might be part of something even bigger, an immense knot in the cosmic web where dark matter and galaxies converge, creating a gravitational anchor for everything around it. Others think it's just one stop on a much longer journey, pulling us toward an even larger structure like the Shapley supercluster, the most massive concentration of galaxies in our observable universe. What makes this phenomenon so captivating isn't just the unanswered questions, it's the sheer audacity of the universe to hide one of its biggest secrets right in our own backyard. Even as our telescopes improve, the zone of avoidance clings to its mysteries, reminding us that sometimes the most important discoveries aren't just about what we can see, but what's still waiting unseen in the dark. Flickering in the constellation Cygnus, about 1,400 light-years from Earth, there's a star that refuses to play by the rules. Known as Tabby's star, officially catalogued as KIC 8462852, this unassuming point of light has baffled astronomers since 2015, when citizen scientists combing through Kepler Space Telescope data noticed something bizarre. Most stars dim in predictable, rhythmic patterns caused by orbiting planets, but Tabby's star doesn't just dim, it plunges. Its light flickers erratically, sometimes dropping by as much as 22%, as if something colossal and misshapen is passing in front of it. And then, just as suddenly, it brightens again, leaving no trace of what caused the darkness. The first explanation to capture the public's imagination was as audacious as it was thrilling. What if we were seeing the shadows of an alien megastructure? Specifically, a Dyson swarm, a hypothetical array of colossal solar collectors built by an advanced civilization to harness the star's energy. The idea wasn't entirely far-fetched. After all, natural phenomena rarely cause such jagged, asymmetric dimming, and the star's sporadic, dramatic drops in brightness seemed almost intentional. For a moment, it felt like humanity might be on the verge of the ultimate discovery, evidence that we're not alone in the universe. But science thrives on skepticism, and astronomers quickly set to work testing other possibilities. Could it be a swarm of comets, a fractured planet's debris field, or perhaps an enormous dust cloud, uneven and clumpy, drifting between the star and our telescopes? Each theory had merits and flaws. Comets might explain some of the dimming, but not the star's long-term, century-spanning fade. Dust fits many of the observations, but the star's infrared signature doesn't quite match what scientists would expect from typical cosmic grit. Even more puzzling, the dimming events aren't periodic. They come and go without warning, sometimes lasting days, sometimes years, like a capricious celestial lighthouse with a broken switch. The latest research points to dust, not ordinary dust, but something exotic, perhaps fine-grained and porous, scattering light in ways we don't yet fully understand. Some scientists speculate the star might be recovering from a catastrophic collision, its system still shrouded in the aftermath. Others wonder if Tabby's star is simply a cosmic oddball, behaving in ways that challenge our models of stellar evolution. But what makes this mystery so captivating isn't just the lack of answers, it's the way Tabby's star forces us to confront how much we still don't know. For all our telescopes and algorithms, the universe keeps surprising us. Whether it's dust, debris, or something far stranger, Tabby's star is a reminder that the cosmos is under no obligation to make sense to us. And that's what makes astronomy so exhilarating. Every unexplained flicker, every anomaly, is a clue waiting to unravel a story we've only just begun to read. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, so many potential homes for life that the odds seem overwhelming. Statistically, intelligent civilizations should be everywhere, and yet when we listen, when we search, the cosmos is eerily silent. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's a question that haunts every search for extraterrestrial intelligence, because if the universe is so hospitable to life, why does it feel like we're alone? One chilling answer is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar levels. The idea is simple. Somewhere along the evolutionary ladder, from simple chemistry to spacefaring civilizations, there's a step so unlikely, so treacherous that almost no species gets past it. The terrifying part, we don't know whether we've already cleared it, or if it's still ahead of us. If the filter is behind us, like the improbable leap from single-celled life to complex organisms, it could explain why we don't see other civilizations. They never made it this far. But if it's ahead, say, self-destruction through nuclear war or uncontrollable artificial intelligence, then our own future might be far more fragile than we'd like to admit. Then there's the zoo hypothesis, a softer but no less unsettling idea. Imagine Earth as a wildlife preserve, deliberately left untouched by advanced civilizations who observe us from a distance, withholding contact until we reach some cosmic milestone. It's a scenario that feels ripped from science fiction, but it raises profound questions about our place in the universe. Are we too primitive to notice the signs, or are we being studied like ants in an interstellar terrarium? But not all explanations are so dire. Maybe we're just looking in the wrong way. Radio signals, the foundation of our SETI efforts, might be as outdated as smoke signals to a civilization that's moved on to quantum communication or other technologies we can't yet fathom. Or perhaps life is incredibly rare and Earth is an accidental oasis in a cosmic desert. Even the concept of civilization might be flawed. What if other intelligent beings exist in forms we can't recognize, their societies so alien that we're essentially blind to them? The Fermi Paradox isn't just about aliens, it's a mirror reflecting our own existential uncertainty. Every possible solution forces us to confront fundamental questions about life's resilience, the longevity of civilizations, and whether intelligence is a cosmic fluke or a destined outcome. With each new discovery, each exoplanet in the habitable zone, each tantalizing signal that turns out to be a quasar, we're not just searching for others. We're trying to understand whether humanity's story is a solitary whisper or one voice in a chorus we've yet to hear. Dark energy is the cosmos' best-kept secret, a force so baffling that even calling it dark feels like an understatement. Picture this: in the late 1990s, two teams of astronomers were studying distant supernova, expecting to confirm that the universe's expansion was slowing down due to gravity's relentless pull. Instead, they found the opposite. The universe wasn't just expanding, it was accelerating, as if some invisible hand had pressed down on the cosmic gas pedal. That discovery flipped astrophysics on its head, revealing that roughly 68% of the universe is made of something we can't see, touch, or even fully comprehend. What makes dark energy so perplexing is how it defies everything we thought we knew. Einstein's equations once included a cosmological constant, a fudge factor he later called his greatest blunder, to explain a static universe. Ironically, that same constant might now describe dark energy's repulsive force, stretching spacetime itself apart. But here's the catch: quantum physics predicts a vacuum energy that could match dark energy's effects, yet the calculated value is off by a factor of 10 to the power of 120. That's not just a rounding error, it's the largest discrepancy in science. The leading theory suggests dark energy could be a property of space itself, a steady, uniform energy density that grows as the universe expands, fueling its own acceleration. But alternatives abound. Maybe it's a dynamic field like the one thought to drive cosmic inflation, evolving over time. Or perhaps gravity behaves differently on cosmic scales, bending the rules we've tested in our own solar system. Some even speculate that dark energy hints at extra dimensions leaking into our universe, a shadow realm influencing reality in ways we're only beginning to glimpse. One thing's certain: dark energy isn't just a mystery, it's a countdown. If acceleration continues, distant galaxies will eventually vanish beyond an invisible horizon, their light never reaching future Earth. The cosmos will grow cold, isolated, and eerily quiet. Yet for now, this enigma keeps scientists racing, probing deeper into the darkness, because understanding dark energy isn't just about mapping the universe's fate, it's about rewriting the very laws that govern existence. High above Earth, hidden in the swirling dance of satellites and space junk, lurks a legend wrapped in shadows: the Black Knight. This elusive object has fueled conspiracy theories for decades, whispered to be an ancient alien satellite silently watching us from orbit. Its story begins in the late 1950s, when newspapers reported strange radio signals allegedly intercepted by both amateur astronomers and military tracking stations. Some claimed these signals were repeating patterns, like coded messages from an intelligence beyond our world. But here's where fact and fiction collide like asteroids in the void. The first concrete sighting came from astronaut Gordon Cooper during his Mercury Atlas 9 mission in 1963. He reported a glowing green object ahead of his capsule, which ground stations allegedly tracked on radar, only for the incident to be swiftly dismissed as a glitch or hallucination. Then came the photographs, grainy images from early space missions, including one from the 1998 STS-88 shuttle mission, showing a peculiar dark object against Earth's curvature. To believers, this was undeniable proof. To scientists, it was likely a thermal blanket lost during a spacewalk. So what's really up there? Modern astronomers point to a simpler explanation: space debris. Earth's orbit is cluttered with thousands of defunct satellites, rocket fragments, and other discarded machinery, some dating back to the dawn of the space age. The Black Knight's supposed orbit matches known debris fields and those eerie radio signals. They've been linked to natural phenomena like pulsars or even early satellite tests conducted in secrecy during the Cold War. Yet the mystery endures because it speaks to something deeper: our fascination with the idea that we're not alone, that somewhere in the silent black something watches. Whether it's a tumbling piece of human history or something far stranger, the Black Knight reminds us that even in our own celestial backyard, the line between myth and reality is thinner than the atmosphere at the edge of space. And sometimes the most compelling stories aren't about what's there, but what we imagine could be. Galaxies may seem like serene islands of stars floating peacefully through the void, but don't let their beauty fool you. The cosmos is a battleground, and the Milky Way is no innocent bystander. It's a predator. Galactic cannibalism, the process where larger galaxies devour smaller ones, isn't some rare cosmic anomaly. It's how galaxies grow. Take Andromeda, our closest galactic neighbor. Right now, it's tearing apart and absorbing a dwarf galaxy called M32, stretching its stars into ghostly streams that spiral into Andromeda's maw. And in about 4 billion years, it'll turn its hunger toward us, colliding with the Milky Way in a slow-motion feast that will reshape both galaxies forever. But this isn't just a story of the future, it's etched in our past. The Milky Way's halo, a vast sphere of ancient stars surrounding our galaxy's disk, is littered with the remnants of cosmic meals. These stars move in chaotic orbits, their paths betraying origins far outside our galaxy. One of the most dramatic examples is the Gaia Sausage, a clump of stars with wild, radial orbits, believed to be the shattered remains of a dwarf galaxy that smashed into the Milky Way 10 billion years ago. The collision was so violent it may have warped our galaxy's disk, leaving ripples in its structure that astronomers are still mapping today. What's truly mind-bending is how these mergers challenge our understanding of galactic evolution. For decades, scientists assumed galaxies grew quietly, steadily accumulating gas and dust to form new stars, but the evidence tells a messier story, one of chaos and collisions. When galaxies merge, their gas clouds slam together, triggering bursts of star formation so intense they can outshine entire galaxies. Yet these feasts also leave scars. The Milky Way's halo contains stars with bizarre chemical compositions, like Omega Centauri, a globular cluster so massive it's likely the stripped core of a devoured galaxy. These celestial fossils hint at a history written in violence, where the serene spiral we see today was forged through countless acts of cosmic consumption. The big question is, what happens to all that stolen material? Smaller galaxies don't just vanish, their stars, gas, and even dark matter are assimilated, becoming part of the larger galaxy's fabric. But the process isn't tidy. Some stars are flung into chaotic orbits while others settle into the disk, blending seamlessly with native stars. Dark matter, invisible and mysterious, mingles with the Milky Way's own halo, leaving only gravitational fingerprints as evidence of its origin. Even the supermassive black holes at the hearts of merging galaxies spiral toward each other, eventually colliding in gravitational waves that ripple across the universe. Galactic cannibalism forces us to rethink what a galaxy even is. They're not static, unchanging islands, they're dynamic, ever-evolving ecosystems shaped by brutal mergers and delicate balances. And as we peer deeper into the cosmos, studying galaxies farther away and further back in time, we're realizing that this violent growth may be the rule, not the exception. So the next time you gaze at the Milky Way's serene band of light, remember, its beauty is the aftermath of chaos, a testament to the universe's endless appetite for reinvention. If the cosmic microwave background is the afterglow of the Big Bang, a baby picture of the universe, then something strange is scribbled in the margins. Meet the axis of evil, an eerie alignment in the radiation left over from the universe's birth that shouldn't exist. When scientists mapped the tiny temperature fluctuations in this ancient light, they expected randomness, a scatter of hot and cold spots reflecting the primordial chaos of the early cosmos. Instead, they found something unsettling. Those fluctuations aren't random at all. They're aligned along a single axis that suspiciously points toward our solar system's ecliptic plane, as if the universe had handed us a mirror and whispered, "You're part of this too." What makes this so disturbing is that it violates one of cosmology's sacred principles, the Copernican principle, the idea that Earth holds no special place in the universe. The CMB should look roughly the same in all directions, a uniform tapestry of variation with no preferred orientation. Yet here we are, staring at a pattern that seems to center on us like celestial breadcrumbs leading back to our doorstep. Some researchers argue it's just a statistical fluke, a trick of perspective in how we process the data. But the odds of such an alignment happening by chance are less than 1 in 1,000, raising uncomfortable questions. Could there be a fundamental flaw in our understanding of the Big Bang? One theory suggests the anomaly isn't cosmic at all. It might be contamination from our own galaxy. Dust in the Milky Way could distort the CMB's signal, imprinting false patterns, but meticulous studies have ruled out most local interference, leaving the mystery intact. Others propose more radical ideas. What if the universe isn't isotropic? What if it has a preferred direction, like a cosmic magnetic field left over from its birth? Some speculative models even flirt with the idea of a pre-Big Bang universe influencing our own, leaving behind fingerprints in the CMB. The axis of evil isn't just a scientific headache, it's a philosophical riddle. If the cosmos really is whispering our address in its oldest light, it forces us to confront a humbling possibility that we might not be incidental observers, but somehow entangled in the universe's deepest workings. Whether it's a measurement glitch or a cosmic clue, one thing's certain: the universe loves a good plot twist, and this one's far from over. Picture a planet untethered, no sunrise, no sunset, just endless darkness stretching in every direction. These are rogue planets, celestial nomads hurtling through the void without a star to call home. Unlike the familiar worlds of our solar system, these wanderers don't orbit anything. They're free agents drifting through the galaxy in perpetual night. Some might have been born this way, collapsing from rogue gas clouds too small to ignite into stars. Others were violently evicted from their birth systems, flung into the abyss by gravitational chaos during their solar system's turbulent youth. Detecting these cosmic orphans is like finding a single flickering candle in a vast, pitch-black desert. Without a star's light to illuminate them, they're nearly invisible. But astronomers have tricks. One method relies on microlensing, a fleeting moment when a rogue planet's gravity bends the light of a distant star, magnifying it like a cosmic magnifying glass. These events last mere hours or days, leaving behind only a subtle blip in the data. Another clue comes from heat. Young rogue planets, still glowing from the energy of their formation, emit faint infrared signatures. In 2020, astronomers using radio telescopes even spotted a Jupiter-sized rogue planet emitting eerie auroras, its magnetic field crackling as it sailed through interstellar space. The numbers are staggering. Estimates suggest there could be billions, even trillions of these lone worlds in our galaxy alone, outnumbering stars by as much as 20 to 1. Some might be frozen wastelands, their surfaces locked in eternal ice. Others, with thick hydrogen atmospheres trapping heat, could harbor warm oceans beneath their surfaces, dark, hidden oases where life might cling in ways we can barely imagine. What's truly humbling is how rogue planets rewrite the rules of planetary science. We used to think planets needed stars to exist, but these wanderers prove the universe is far more creative. They challenge our definitions, blur the line between planet and star, and remind us that for every cosmic rule we think we've cracked, there's an exception drifting silently through the dark, waiting to be found. In the vast cosmic web where galaxies cluster like glittering cities, there's a place so empty it defies logic, a black nothingness stretching 330 million light-years across. Welcome to the Boötes Void, a gaping hole in the universe so vast you could fit 60 Milky Ways side by side and still find nothing but darkness. Dubbed the Great Nothing by astronomers, this void isn't just a quiet corner of space, it's a cosmic ghost town. A vacuum so extreme it challenges everything we thought we knew about how the universe structures itself. When scientists first stumbled upon the Boötes Void in the 1980s, the discovery sent shockwaves through astrophysics. According to our best models, the universe's large-scale structure should resemble a sponge, filaments of galaxies woven around moderately empty bubbles. But the Boötes Void isn't a bubble, it's a cavern. While most voids contain a handful of galaxies, this one holds only 60 in its terrifying expanse, making it one of the emptiest regions ever observed. To put that in perspective, a typical volume of space that size should host at least 2,000 galaxies. So where did they all go? The leading theories are as unsettling as the void itself. One possibility is that the Boötes Void formed from smaller voids merging over billions of years, like soap bubbles combining into one enormous void. But even that explanation struggles to account for the sheer scale of this nothingness. Another idea suggests it might be evidence of an ancient collision with a parallel universe, a cosmic bruise left behind by something beyond our reality. While that sounds like science fiction, it's a reminder of how little we truly understand about the fabric of existence. Oddly enough, the few galaxies trapped in this void have their own mysteries. They're not evenly scattered but clustered in a narrow band, as if huddling together for warmth in an endless winter. Some show strange bursts of star formation, their gas clouds collapsing into stars at rates far higher than expected for such an isolated environment. It's as if the void itself is squeezing these galaxies, wringing out whatever vitality they have left. What makes the Boötes Void so chilling isn't just its emptiness, it's the way it forces us to question our cosmic maps. If voids like this exist, could there be others even larger, lurking just beyond the limits of our telescopes? And if the universe can produce such staggering desolation, what does that mean for our theories of dark matter, galaxy formation, and the very balance of the cosmos? The Boötes Void is more than a curiosity. It's a cosmic riddle written in negative space, daring us to look deeper into the dark. At the edge of the observable universe, where light has traveled nearly 13 billion years to reach us, there are objects so luminous they outshine entire galaxies, yet they're no larger than our solar system. These are quasars, the universe's ultimate powerhouses, where supermassive black holes turn gravity into light on an unimaginable scale. Imagine taking all the energy of 100 Milky Ways and compressing it into a single, blazing point. That's the raw intensity of a quasar, a beacon so bright we can see it from across the cosmos. What makes quasars truly extraordinary isn't just their brilliance, it's what fuels them. At their core lies a supermassive black hole, billions of times heavier than our Sun, surrounded by a swirling disk of superheated gas known as an accretion disk. As matter spirals toward the black hole's event horizon, friction heats it to millions of degrees, unleashing torrents of radiation across the electromagnetic spectrum. But here's the twist: while black holes are famous for trapping light, quasars prove they can also be the universe's brightest lamps. The energy released isn't coming from the black hole itself, it's the dying scream of matter being torn apart just outside the point of no return. Quasars were far more common in the early universe, and that's no accident. The cosmos was smaller, denser, and packed with fresh gas, perfect conditions for feeding monstrous black holes. As these behemoths gorged themselves, their quasars became cosmic lighthouses, shining through the primordial fog. Their light carries fingerprints of that ancient era, revealing how the first galaxies grew and how the opaque hydrogen fog of the early universe became transparent, a process called reionization. Without quasars lighting the way, we'd know far less about the universe's infancy. Yet the most baffling aspect of quasars isn't their power, but their efficiency. The laws of physics say only about 10% of matter's energy should be converted to light as it falls into a black hole. But some quasars blow past that limit, achieving efficiencies that defy textbook models. One theory suggests their black holes might be spinning at near-light speeds, twisting space-time itself into an energy-generating dynamo. Others propose magnetic fields acting like cosmic particle accelerators, funneling energy outward in focused jets that stretch for millions of light years. These jets, visible in radio telescopes, can punch through entire galaxies, shaping their evolution like a celestial sculptor. Today, most quasars have gone quiet, their fuel depleted, their black holes slumbering. But their legacy lives on. The supermassive black holes they once powered now anchor galaxies like our own, silent reminders of a more violent, luminous past. And occasionally, when a star or gas cloud drifts too close, these sleeping giants wake up not as quasars but as their smaller cousins, active galactic nuclei. Quasars teach us a paradoxical truth. Black holes aren't just destroyers, they're also creators, shaping galaxies, seeding the universe with heavy elements, and lighting the darkness so we can peer back to the dawn of time. They're proof that even the most terrifying forces in nature can become, against all odds, sources of illumination. In the cold expanse of interstellar space, far beyond the orbits of Neptune and Pluto, two spacecraft were caught in a cosmic slow-motion mystery. NASA Pioneer 10 and 11 probes, launched in the early 1970s to study the outer planets, should have been drifting toward the stars with predictable precision. But by the 1980s, something was clearly wrong. Both probes were decelerating slightly, as if an invisible hand was gently tugging them back toward the Sun. This tiny but persistent anomaly, just a fraction of a nanometer per second squared, might sound negligible. But in the precise world of orbital mechanics, where a single misstep can send a probe millions of miles off course, it was enough to send shockwaves through the scientific community. At first, theories ranged from the mundane to the revolutionary. Maybe it was gas leaking from the probe's thrusters, or the faint pressure of sunlight pushing against their large antenna dishes. But when engineers accounted for every conceivable known force, the anomaly remained. That's when whispers of new physics began, perhaps an undiscovered gravitational effect, or even a flaw in Einstein's theory of general relativity. Some researchers dared to suggest the probes might be encountering a mysterious form of dark matter, or that the universe's expansion was exerting a subtle drag on the spacecraft. For decades, the Pioneer anomaly became a tantalizing riddle, a glitch in the cosmic code that promised to rewrite the textbooks. Then, in 2012, a team of researchers proposed a far simpler explanation: heat. The Pioneers, powered by radioactive plutonium, generated warmth that radiated unevenly from their bodies. Most spacecraft correct for this with thrusters, but the Pioneers were spin-stabilized like gyroscopes with no active propulsion to balance the effect. When scientists meticulously modeled how infrared radiation would bounce off the probe's dish-shaped antennas, they found it created just enough recoil to explain most of the anomaly. Case closed, not quite. While heat resolved the bulk of the mystery, some discrepancies lingered, particularly for Pioneer 11. The numbers still didn't add up perfectly, leaving room for one last whisper of doubt. What makes the Pioneer anomaly so compelling isn't just the science, it's the lesson it teaches about curiosity. For 30 years, this tiny deviation haunted astronomers, a reminder that even our most trusted models of the universe might be incomplete. It's a story of how science self-corrects, how the relentless pursuit of an answer can lead us from wild speculation to mundane truth, and sometimes back to questions we still can't quite answer. Today, as newer missions like New Horizons streak toward the edge of the solar system, they carry with them the legacy of the pioneers, a cautionary tale about the universe's endless capacity to surprise us, even in the emptiest corners of space. In October 2017, astronomers spotted something that had never been seen before, a visitor from another star system, named Oumuamua, Hawaiian for scout. This mysterious object tumbled past the sun at blistering speeds, its trajectory telling a clear story: it wasn't from here. But what followed wasn't just a routine discovery, it was a firestorm of scientific debate, fueled by Oumuamua's bizarre behavior. First, there was its shape. Unlike any asteroid or comet we've seen, it appeared strangely elongated, perhaps 10 times as long as it was wide, tumbling through space like a cosmic cigar. Then came the real shocker. As it raced away from the sun, it sped up slightly, as if pushed by an unseen force. Mainstream astronomers pointed to outgassing, a common phenomenon where comets, warmed by the sun, release jets of gas that act like natural thrusters. But there was a problem. Telescopes detected no gas, no dust tail, no icy glow typical of comets. Without these telltale signs, the acceleration became a puzzle. Enter Harvard astrophysicist Avi Loeb, who proposed a theory that sent ripples through the scientific community. What if Oumuamua wasn't a natural object at all? His suggestion that it could be a piece of alien technology, perhaps a light sail propelled by starlight, was met with equal parts fascination and skepticism. Critics argued that extraordinary claims require extraordinary evidence, and Oumuamua's oddities could still fit natural explanations. Maybe it was made of exotic hydrogen ice, vaporizing invisibly in sunlight. Or perhaps its surface was unusually reflective, magnifying subtle pressure from solar photons. Others speculated it could be a fractured shard from a planet torn apart by its star, explaining its jagged shape and lack of visible outgassing. Each theory had holes, but they underscored a deeper truth. We'd never seen anything like this before, and our frameworks for understanding it were still provisional. What makes Oumuamua so compelling isn't just the mystery of its origin, it's the way it exposes the limits of our cosmic vocabulary. When faced with something truly alien, we scramble to fit it into familiar boxes: comet, asteroid, spacecraft. But the universe isn't obligated to follow our categories. Whether Oumuamua was a bizarrely shaped rock, a fragment of an ancient collision, or something far stranger, its fleeting visit was a humbling reminder. Out there in the dark, the rules might be wilder than we've dared to imagine. Just beyond Neptune's orbit, the Kuiper belt stretches like a frozen graveyard of cosmic leftovers, icy rocks and dwarf planets left over from the solar system's birth. But out here, where sunlight is a faint memory, something strange happens. The belt doesn't fade gradually into the void, it ends abruptly, as if sliced by an invisible blade. Astronomers call this boundary the Kuiper Cliff, and its existence is a puzzle that's rewriting our understanding of the solar system's edge. The math doesn't add up. Based on models of planetary formation, the Kuiper belt should teem with objects for hundreds of astronomical units beyond its current edge. Yet past 50 astronomical units, around 7.5 billion kilometers from the Sun, the number of detectable objects drops off a cliff. It's not just a slight decline, it's a sheer void where there should be thousands of icy bodies. Why would the solar system's debris field suddenly vanish? One tantalizing answer points to an unseen giant planet 9, a hypothetical world up to 10 times the mass of Earth lurking in the outer darkness. The idea isn't as far-fetched as it sounds. In the early 20th century, irregularities in Neptune's orbit led to the discovery of Pluto. Now, history might be repeating itself. Computer simulations show that a distant, massive planet could sculpt the Kuiper Cliff by gravitationally shepherding objects into clustered orbits or flinging them into the abyss. Some of these ejected objects might even become rogue planets drifting through interstellar space. But Planet 9 isn't the only suspect. Alternative theories suggest the cliff could be a relic of the solar system's violent infancy, a fossilized edge where the protoplanetary disk was abruptly truncated by a passing star or the gravitational pull of the Milky Way itself. Others propose more exotic explanations, like the influence of primordial black holes, tiny, ancient relics of the Big Bang that could warp the orbits of Kuiper belt objects without emitting any light. The Kuiper cliff isn't just a curiosity, it's a cosmic crime scene, and every missing object is a clue. Whether the culprit is a hidden planet, a long-vanished stellar intruder, or something even stranger, this boundary forces us to confront how little we truly know about our own celestial backyard. The outer solar system, it seems, still has secrets to spill, and the Kuiper cliff is just the beginning. The universe is expanding, that much we know, but how fast? That's where things get complicated, and where one of modern cosmology's biggest headaches begins. Meet the Hubble tension, a stubborn discrepancy that's forcing scientists to question whether we've misunderstood the cosmos itself. On one side, we have meticulous measurements of the early universe's afterglow, the cosmic microwave background, painting a precise picture of how fast space should be stretching. On the other, observations of nearby stars and supernova tell a different story, one where the universe is expanding noticeably faster than those ancient echoes predict. The gap might sound small, just a few kilometers per second per megaparsec, but in the high-stakes world of cosmology, it's a chasm. And bridging it could mean rewriting the rules we thought governed everything from dark energy to the fate of the universe. So how did we get here? The Hubble constant, the number describing the universe's expansion rate, has been astronomy's holy grail since Edwin Hubble first noticed galaxies racing away from us in the 1920s. For decades, refining this number was a straightforward, if painstaking, task. Measure distances to faraway objects, track their movement, and calculate the rate. But as techniques improved, something odd emerged. Two methods, both incredibly precise, started giving different answers. The first relies on the cosmic microwave background, the faint radiation left over from the Big Bang. By studying its subtle fluctuations with satellites like Planck, scientists extrapolate how quickly the infant universe grew, arriving at an expansion rate around 67 kilometers per second per megaparsec. The second method skips the ancient light entirely, using pulsating stars called Cepheids and brilliant stellar explosions known as Type Ia supernova as cosmic yardsticks. These local measurements consistently land closer to 73, nearly 10% higher. At first, astronomers hoped the gap was a fluke, a measurement error, or perhaps a systematic glitch in one of the methods. But as data piled up from independent teams using different telescopes and techniques, the tension only grew. The James Webb Space Telescope's razor-sharp infrared vision recently confirmed the discrepancy wasn't just Hubble's aging eyes playing tricks. Even gravitational waves, the ripples in spacetime from colliding neutron stars, have joined the debate, offering a third way to measure expansion, and muddying the waters further with results that land somewhere in between. Now the real fun begins, figuring out why. Some theorists argue this isn't just a technical hiccup, it's a sign our standard model of cosmology, the lambda-CDM framework, might be missing a crucial ingredient. Could dark energy evolve over time, growing stronger and accelerating expansion faster than we thought? Might there be a new, unknown particle, a cousin to the neutrino, adding extra energy to the early universe and throwing off our calculations? Or is the answer even wilder, like evidence of a shadow universe parallel to ours, subtly tugging at spacetime? The more mundane explanations, hidden biases in our measurements, or overlooked quirks in how supernova explode haven't been ruled out, but with each passing year they look less likely. What makes the Hubble tension so thrilling is what it represents: a crack in the foundation of cosmology, a chance to discover something revolutionary. Whether it's new physics, a flaw in our cosmic yardsticks, or something no one's even dreamed up yet, Resolving this puzzle won't just tweak a number in a textbook, it could reshape our understanding of reality itself. And until we crack it, the universe will keep expanding, mysteries and all, just a little faster than we expected. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, white holes would be their cosmic opposites, gushing fire hydrants of matter and energy, spewing out anything that dares to approach. These hypothetical objects, first dreamed up as mathematical curiosities in Einstein's theory of general relativity, are essentially black holes running in reverse. Where a black hole's event horizon is a one-way door into oblivion, a white hole's would be an exit with no entrance, violently ejecting material instead of trapping it. Picture a celestial fountain where water arcs upward but never falls back down, defying gravity itself. That's the baffling essence of a white hole, a place where the universe says no admittance in bold cosmic letters. The idea emerges from the equations of general relativity, which are famously time-symmetric, meaning they work just as well backward as forward. Flip a black hole's timeline and you get a white hole, a region of space-time where matter bursts outward but nothing can enter. Some theories even suggest white holes could be the other end of a black hole's tunnel, connected by a wormhole in a cosmic game of interstellar plumbing. It's a tantalizing thought, black holes swallowing matter in one corner of the universe, white holes spitting it out somewhere else. But here's the catch. While black holes are littered across the cosmos, confirmed by everything from gravitational waves to the shadow of M87's behemoth, white holes remain stubbornly theoretical. Not a single one has ever been observed, so why haven't we found one? For starters, white holes might be spectacularly unstable. Unlike black holes, which form naturally when massive stars collapse, white holes would require some incredibly exotic conditions to exist, perhaps a black hole transitioning into a white hole after evaporating due to Hawking radiation, or a spontaneous eruption of spacetime itself. Even then, most models suggest they'd last only a fraction of a second before collapsing into a black hole or dissipating entirely. There's also the problem of entropy. The universe tends toward disorder, and a white hole's orderly gush of energy seems to violate that principle unless there's some hidden mechanism balancing the scales. Yet the absence of evidence hasn't stopped physicists from speculating. Some propose that gamma-ray bursts, those blindingly intense flashes of energy detected across the universe, could be white holes flickering into existence and vanishing just as quickly. Others wonder if the Big Bang itself might have been a white hole event, a primal eruption of space-time and matter from some unknowable predecessor universe. It's a wild idea, but that's the allure of white holes. They force us to wrestle with the universe's most extreme possibilities, where time bends backward and the fabric of reality frays at the edges. What makes white holes so fascinating isn't just their defiance of common sense. It's how they reveal the playful, almost mischievous side of theoretical physics. They remind us that the universe's rulebook might have pages we haven't even glimpsed yet, where the impossible becomes merely improbable. And until we find one, or prove they can't exist, they'll remain one of cosmology's most tantalizing what-ifs, a ghostly counterpart to the darkness we know so well. Hidden within the faint glow of the cosmic microwave background, the universe's oldest light lies a chilling anomaly. Stretching across the constellation Eridanus, a vast region of space appears eerily colder than its surroundings, as if someone turned down the cosmic thermostat. This cold spot isn't just a minor fluctuation. It spans a staggering 1.8 billion light-years, making it one of the largest individual structures ever identified. And the most unsettling part, it shouldn't exist. According to our best models of the early universe, the cosmic microwave background should exhibit small, random temperature variations like static on an old television, reflecting the primordial density fluctuations that seeded galaxy formation. But the cold spot is an outlier, a deviation so extreme that the odds of it occurring naturally are less than 1 in 50. At first, astronomers assumed it was just a trick of the data, a glitch in the measurements from the Planck satellite or an effect of foreground interference. But repeated observations confirmed it was real, sparking a frantic search for explanations. One leading theory suggests the cold spot might be the fingerprint of a supervoid, an enormous, nearly empty region of space where matter is sparser than average. In an expanding universe, light passing through such a void would lose energy, a phenomenon known as the integrated Sachs-Wolf effect, potentially creating a cold imprint in the CMB. But here's the catch: the Eridanus supervoid, discovered in 2015, doesn't seem large or empty enough to explain the cold spot's intensity. It's like trying to cool a swimming pool with a single ice cube. The numbers just don't add up. That's where things get speculative. Some cosmologists have proposed far more radical ideas, like the cold spot being a collision scar between our universe and another bubble universe in the multiverse. If another cosmos brushed against ours during inflation, the exponential expansion of spacetime after the Big Bang, it could have left behind a thermal irregularity, a bruise on the fabric of reality. While this idea leans heavily into theoretical territory, it's not pure fantasy. Certain models of eternal inflation naturally predict such collisions with observable consequences. Yet skeptics argue the cold spot might still be a statistical fluke, an improbable but not impossible roll of the cosmic dice. After all, in a universe as vast as ours, even the unlikeliest events can occur somewhere. Others suggest more mundane explanations, like unforeseen systematic errors in how we process CMB data or undiscovered large-scale structures warping our observations. The debate underscores a deeper truth: the cold spot isn't just a puzzle, it's a stress test for cosmology itself. What makes the Eridanus supervoid so captivating isn't just its mystery, it's the way it forces us to question the limits of our knowledge. Whether it's evidence of a parallel universe, a gap in our understanding of voids, or simply a cosmic illusion, this chilling anomaly reminds us that the universe still has the power to surprise, confound, and humble us. And until we crack its code, it remains one of the most tantalizing enigmas written in the sky. Of all the cosmic monsters lurking in the universe, few are as terrifyingly unpredictable as magnetars, neutron stars that take the concept of a magnetic field and crank it up to apocalyptic levels. To grasp just how extreme these objects are, picture this: a magnetic field so powerful it could strip the information off every credit card on Earth from halfway across the galaxy. We're talking about magnetic forces a quadrillion times stronger than our planets, so intense they twist the very fabric of spacetime around them, creating conditions so alien that physicists still struggle to model them. Magnetars are born from violence when a massive star, at least 10 times heftier than our Sun, exhausts its fuel and collapses in a supernova. Its core doesn't just become a neutron star, it becomes a twisted, hyper-magnetized relic. The process is like spinning a ball of tangled rubber bands tighter and tighter until they snap, except here, the rubber bands are the star's magnetic fields, and the snap unleashes energy equivalent to 1 billion atomic bombs. This isn't just theoretical. In 2004, a magnetar 50,000 light-years away released a blast of gamma rays so powerful it briefly ionized Earth's upper atmosphere, despite being halfway across the galaxy. What makes magnetars truly bizarre are their starquakes, think earthquakes, but on a cosmic scale. As the neutron star's rigid crust adjusts to the unimaginable strain of its own magnetism, it fractures, sending ripples through the star that release bursts of X-rays and gamma rays. These aren't gentle tremors. A single crack in a magnetar's surface can unleash more energy than our Sun emits in a century. In 1998, one such event, detected from a magnetar in the constellation Aquila, temporarily blinded every X-ray satellite in orbit, overwhelming their sensors like a camera staring into a supernova. The real mystery, though, is how these magnetic fields get so strong in the first place. One theory suggests it's a cosmic dynamo effect. The newborn neutron star's rapid rotation, combined with convection currents in its superfluid interior, amplifies its magnetic field to ludicrous levels. Others propose quantum mechanics plays a role, with exotic particles aligning in ways that turbocharge the magnetism. But here's the catch. Even our best models struggle to explain why some neutron stars become magnetars while others, like pulsars, have relatively tame magnetic fields. It's as if the universe rolled a dice and a handful of neutron stars landed on cosmic nightmare mode. Then there's the space-time warping. A magnetar's magnetic field is so intense it doesn't just bend light, it distorts the quantum vacuum, the froth of particles that constantly pop in and out of existence at the smallest scales. Under these conditions, empty space itself becomes birefringent, splitting photons into two paths like a cosmic prism. Some physicists speculate that if you could survive long enough to get close to a magnetar, which you couldn't, its gravity would shred you long before. You might witness physics textbooks rewritten in real time, with atoms stretched into needle-thin shapes and chemical bonds behaving in ways that defy intuition. Yet for all their destructive potential, magnetars might hold clues to some of the universe's biggest puzzles. Their extreme environments mimic conditions that existed a fraction of a second after the Big Bang, offering a natural lab for testing high-energy physics. Some researchers even think magnetar eruptions could explain fast radio bursts, those enigmatic cosmic signals that have puzzled astronomers for years. Whether as cosmic destroyers or celestial Rosetta Stones, magnetars are a reminder that the universe doesn't just push boundaries, it obliterates them, leaving us scrambling to make sense of the wreckage. We like to think we've catalogued the universe's ingredients, stars, planets, galaxies, and the dark matter holding them together. But there's a glaring gap in the cosmic inventory. Half the universe's normal matter, the stuff that makes up everything we can see and touch, has gone missing. This isn't dark matter we're talking about. It's the ordinary protons and neutrons, known collectively as baryons, that should be everywhere but somehow slipped through our observational nets. For decades, astronomers scratched their heads over this discrepancy. If the math said the baryons had to be there, why couldn't we find them? The breakthrough came when scientists realized they'd been looking in the wrong places. Instead of hunting for stars or gas clouds, they turned their attention to the faint, gossamer threads of the cosmic web, the vast network of filaments connecting galaxies across the void. These filaments, made of superheated gas, are so diffuse they're nearly invisible, glowing only in the most energetic X-rays. It's like trying to spot a single lit match in a foggy forest. But with space telescopes like Chandra and XMM Newton, researchers finally detected this hidden reservoir, solving part of the missing baryon puzzle. The gas wasn't missing, it was just hiding in plain sight, woven into the universe's scaffolding. Yet the mystery isn't fully solved. While these filaments account for a significant chunk of the lost baryons, there's still a stubborn fraction unaccounted for. One theory suggests the remaining matter might be lurking in even harder to detect forms, perhaps as ultra-diffuse clouds of warm gas floating between galaxies, too cool to emit X-rays but too warm to show up in radio surveys. Another possibility is that some baryons have been pushed out of galaxies entirely by the fierce winds of supernova explosions or supermassive black holes, scattered into intergalactic space like dust in a cosmic hurricane. The stakes are higher than just balancing a ledger. These missing baryons are critical to understanding how the universe evolved. They're the raw material for stars, planets, and life itself, and their distribution holds clues to how galaxies form and grow. If we can't track them all down, it's like trying to reconstruct a cake recipe when half the flour has mysteriously vanished. The search has even led to creative detective work, like studying how light from distant quasars dims as it passes through these invisible gas clouds, revealing their presence like a cosmic shadow puppet show. What makes this enigma so compelling isn't just the scientific challenge. It's the humbling reminder of how much we still don't know about the universe's most basic building blocks. Even the so-called normal matter, the stuff we're made of, can defy our best efforts to pin it down. Whether the remaining baryons are hiding in undiscovered corners of the cosmic web or have been transformed into some elusive state, their disappearance is a puzzle that keeps astronomers up at night. And until we crack it, we're left with a universe that's still full of surprises, even in its most ordinary ingredients. Nestled in the constellation Monoceros, about 2,300 light-years from Earth, there's a cosmic structure so precise it looks like it was drafted with a ruler and protractor. The Red Rectangle Nebula, aptly named for its striking geometric appearance, is one of the most visually bizarre objects in the galaxy. Unlike the chaotic, billowing clouds of most nebulae, this one presents an almost architectural symmetry. Two conical jets of gas and dust forming a near-perfect X-shape, framed by a rectangular glow of crimson light. It's as if the universe, known for its love of randomness, decided to flex its artistic muscles in a moment of mathematical precision. But the red rectangle's beauty is more than skin deep. Its vibrant color, a deep ruby hue, comes from an exotic cocktail of hydrocarbons unlike anything found in typical nebulae. Most glowing nebulae shine due to ionized gas excited by nearby stars, but here the light is emitted by something far stranger, complex organic molecules called polycyclic aromatic hydrocarbons, or PAHs. These intricate carbon-based compounds, which resemble microscopic chicken wire, fluoresce under ultraviolet light, painting the nebula in shades of red. The presence of these molecules is puzzling enough, but their abundance here is downright confounding, suggesting processes at work that defy our understanding of how such compounds form in space. At the heart of this enigma lies a binary star system, HD 44179, locked in a slow dance of mutual destruction. One of the stars has already exhausted its nuclear fuel, shedding its outer layers in a series of eruptions that created the nebula's distinctive shape. But here's the twist: the symmetry of the red rectangle shouldn't be possible. When stars expel material, it usually billows outward in uneven, chaotic waves. Think of a balloon deflating in random bursts. Yet somehow, this dying star's ejections have been sculpted into near-perfect cones, their edges razor-sharp. One theory suggests the star's companion acts like a cosmic potter's wheel, its gravity shaping the outflow into geometric precision. Another idea posits that a dense disk of dust around the stars funnels the material into these precise jets, like sand art in zero gravity. But the weirdness doesn't stop there. The red rectangle's structure isn't static, it's evolving and fast. Observations spanning decades reveal that its lobes are expanding at speeds of over 100,000 kilometers per hour, while intricate ladder-like rungs, dubbed spokes, stretch across its interior. These features, which resemble the ribs of an umbrella, might be shock waves from periodic outbursts of the central star, frozen in time as they race outward. Yet no current model fully explains why these shocks would organize themselves into such regular, spaced intervals. It's as if the nebula is vibrating like a tuning fork, emitting cosmic harmonics we're only beginning to detect. What makes the red rectangle so mesmerizing isn't just its defiance of expectations, it's the questions it raises about the universe's hidden order. Is this geometric perfection a rare fluke or a sign of deeper, undiscovered physics governing how stars die? Could those complex hydrocarbons hint at probiotic chemistry occurring in the void, seeding the cosmos with the building blocks of life? And if so, how many other eerily perfect structures are out there waiting to be found? For now, the red rectangle remains a masterpiece of celestial geometry, a reminder that even in the cold expanse of space, nature has a flair for the artistic and the inexplicable. Saturn's North Pole is hiding a geometric marvel that defies everything we know about planetary weather, a colossal hexagon wider than two Earths, etched into the planet's atmosphere like a cosmic honeycomb. This six-sided storm has raged for at least 4 decades, possibly much longer, its razor-sharp edges standing defiant against the chaotic turbulence of Saturn's gaseous seas. Unlike the spiraling hurricanes of Earth or Jupiter's raging oval storms, this structure is eerily precise, as if drawn by the hand of some celestial mathematician. How does a planet known for its swirling, chaotic atmosphere produce something so rigidly geometric? The answer lies in a dizzying dance of physics that even Earth's most advanced labs can't quite replicate. At first glance, the hexagon seems like an optical illusion, a trick of perspective, but spacecraft like Cassini have confirmed its reality, capturing stunning images of this atmospheric polygon churning with winds screaming at 320 kilometers per hour. The most startling feature isn't just its shape, it's the stability. While Earth's weather systems dissipate in days or weeks, Saturn's hexagon persists, anchored to the planet's rotation like a fixed gear in a cosmic engine. This endurance hints at something deeper at work, a fundamental interplay between fluid dynamics and planetary forces that scientists are only beginning to decode. One leading theory points to the quirks of rotating fluids. In lab experiments, when liquids are spun at high speeds, they can form polygons, squares, triangles, even octagons depending on the conditions. Saturn's atmosphere, a deep ocean of hydrogen and helium, behaves like a supercharged version of these experiments. As the gas swirls around the pole, shear forces between different layers might create standing waves like vibrations in a drumhead, locking the storm into a hexagonal pattern. But here's the catch: Earth labs can't spin fluids fast enough to match Saturn's scale. The planet's rapid rotation, a day lasts just 10.5 hours, combined with its lack of solid continents to disrupt airflow, creates conditions impossible to fully simulate on our world. It's like trying to recreate a tsunami in a bathtub, yet the hexagon's mysteries go deeper. Infrared observations reveal it's not just a surface feature. It towers hundreds of kilometers tall, a towering wall of gas extending far into Saturn's stratosphere. Even more bizarre, the hexagon appears to change color with Saturn's seasons, shifting from golden hues to bluish tones as sunlight waxes and wanes over its 30-year orbit. This suggests the structure isn't just a fluid dynamic fluke. It's interacting with the planet's chemistry and energy flow in ways we don't yet understand. Some researchers speculate that the hexagon might even be a window into Saturn's hidden interior, a surface manifestation of deeper, slower currents churning beneath the clouds. What makes the Saturn hexagon so captivating isn't just its otherworldly symmetry. It's the way it forces us to rethink the boundaries of planetary science. On Earth, nature favors curves and spirals. On Saturn, geometry reigns supreme. Whether it's a fleeting alignment or a permanent fixture of gas giants, this six-sided enigma reminds us that the universe has a flair for the unexpected, crafting patterns where we least expect them. And until we can peer deeper into Saturn's swirling depths, the hexagon will remain one of the solar system's most tantalizing puzzles, a shape etched into the sky, daring us to unravel its secrets. The Moon has always been Earth's silent companion, a barren rock pockmarked with craters, lacking the churning metal core that powers our planet's magnetic shield. So imagine the shock when Apollo astronauts brought back lunar rocks in the 1960s and 70s, only for scientists to discover something impossible. These ancient stones bore the ghostly imprint of a magnetic field. Not just any field, but one nearly as strong as Earth's at times. This shouldn't have been possible. Planetary magnetism requires a molten, conductive core in constant motion, a dynamo effect where swirling liquid metal generates a magnetic field. But the Moon's core is tiny, just a fraction of its size, and long thought to have cooled into a dormant lump of iron billions of years ago. Yet the evidence was undeniable. Something had magnetized these rocks, and whatever it was, it rewrote the story of our closest celestial neighbor. To grasp the scale of this mystery, think of magnetism like a cosmic battery. Earth's dynamo hums along thanks to its massive molten core, where heat from radioactive decay and leftover planetary formation keeps the metal churning. Mars, smaller and cooler, lost its global magnetic field eons ago, leaving its atmosphere vulnerable to being stripped away by solar winds. The Moon, with just 1% of Earth's mass, shouldn't have stood a chance. Yet those Apollo samples revealed minerals like magnetite locked in place by fields reaching up to 70 microteslas, roughly half of Earth's current surface magnetism. The question isn't just how this happened, but how it persisted for possibly over 1 billion years, defying every model of lunar evolution. One radical theory points to an ancient cosmic collision. Early in the solar system's history, the Moon might have been spinning much faster, its small core stirred into temporary dynamo action by the sheer force of rotation. Imagine spinning a basketball on your finger. The faster it twirls, the more stable it becomes, but slow it down and it wobbles and falls. The Moon's dynamo could have worked the same way, its rapid spin keeping the core churning until tidal forces from Earth gradually braked it, letting the core solidify and the field fade. There's just one problem. Even at its fastest, the Moon's core might not have been large enough to sustain such a strong field for so long. Another possibility is that the Moon's magnetism wasn't homegrown at all but borrowed. Earth's own magnetic field could have stretched like an invisible umbrella over its satellite, imprinting its signature on the lunar surface during close encounters early in their shared history. Think of it as celestial induction, the way a guitar pickup converts string vibrations into sound. The Moon might have temporarily resonated with Earth's magnetism. But this, too, has flaws. The Moon's field signatures don't always align with Earth's past magnetic behavior, suggesting something more complex was at play. Then there's the wild card, impact-driven magnetism. During the Moon's violent youth, colossal asteroids and comets slammed into its surface with enough force to liquefy rock, creating vast magma oceans. These impacts could have triggered short-lived, localized magnetic fields as the molten material swirled in the chaos, like stirring a cup of coffee with a spoon. Some scientists even propose that the Moon's crust itself, rich in iron-bearing minerals, might have generated fleeting fields when heated by these collisions. It's a patchwork explanation, more of a temporary spark than a sustained glow, but it could account for some of the inconsistencies in the rock record. The deeper we dig into this enigma, the more it challenges our understanding of how magnetism works not just on the Moon but across the cosmos. If something as small and seemingly inert as the Moon once harbored a robust magnetic field, what does that mean for exoplanets or even asteroids? Could magnetic shielding be more common in the universe than we thought, offering fleeting protection to worlds we once assumed were barren? For now, the Moon keeps its secrets. Future missions like NASA's planned Lunar Vertex rover aim to study magnetic anomalies directly, mapping the ghostly remnants of this ancient field. Until then, those magnetized Apollo rocks sit in labs, silent witnesses to a time when the Moon was far more than a dead rock. It was a dynamic world with its own invisible shield, a cosmic mystery wrapped in dust and shadows. Hidden in the vast cosmic tapestry, there's a structure so immense it shouldn't exist, the Hercules Corona Borealis Great Wall, a galactic behemoth stretching a mind-bending 10 billion light-years across. To put that into perspective, this thing is so colossal it spans roughly 1/9 of the observable universe. That's like a single cloud covering half the sky, defying every rule we thought governed how matter organizes itself after the Big Bang. The story begins in 2013, when astronomers mapping gamma ray bursts, the brightest explosions in the universe, noticed an eerie pattern. These bursts weren't scattered randomly, they clustered along a curved ribbon stretching across the constellations Hercules and Corona Borealis. At first, researchers assumed it was a fluke, a trick of perspective. But as more data poured in, the impossible became undeniable. This wasn't just a random alignment. It was evidence of an underlying structure, a sprawling superstructure of galaxy clusters and dark matter woven together on a scale that shattered previous records. Here's the problem: according to our best models of cosmology, structures this huge shouldn't be possible. The Big Bang's afterglow, the cosmic microwave background, reveals a universe that started off remarkably smooth with only tiny density fluctuations. Over billions of years, gravity amplified those fluctuations, pulling matter into the filaments and voids of the cosmic web we see today. But there's a limit to how big those structures should grow, dictated by the speed of light and the age of the universe. The Hercules Corona Borealis Great Wall doesn't just push that limit, it obliterates it, stretching far beyond what theorists thought feasible. It's like finding a single tree taller than Mount Everest, growing in a forest where everything else follows the rules. So how did it form? One possibility is that we're seeing a rare statistical anomaly, a cosmic jackpot where several smaller structures aligned in just the right way to mimic something larger. But the odds of that are vanishingly small. Another, more radical idea is that this wall is a relic of the universe's infancy, a fossilized ripple from a time before inflation, the exponential expansion thought to have smoothed the early cosmos. If those ripples weren't perfectly even, they could have seeded gargantuan structures like this one. There's even speculation that the wall might hint at something beyond our observable universe, a shadow of a neighboring cosmic bubble brushing against our own. Yet the most humbling part isn't just the wall's size, it's how it forces us to confront the limits of our knowledge. For decades, cosmologists worked under the assumption that, on the largest scales, the universe is homogeneous. The Hercules Corona Borealis Great Wall throws that principle into question, suggesting there might be structures out there so vast they rewrite the rules of cosmic geography. And with every new telescope, every deeper survey of the sky, we're left wondering, is this wall unique, or is it just the first of many cosmic titans waiting to be discovered? What makes this enigma so captivating isn't just the science, it's the sheer audacity of the universe to defy expectation. Whether it's a flaw in our models, a window into the multiverse, or simply a reminder that nature loves an underdog, the Hercules Corona Borealis Great Wall stands as one of cosmology's greatest puzzles. And until we unravel its secrets, it looms over us, a silent, sprawling challenge etched across the stars. Imagine stepping outside on a moonless night, far from city lights, and seeing a faint, ghostly pyramid of light stretching upward from the horizon. Not the Milky Way's starry band, but something subtler, almost ethereal. This is the zodiacal light, a celestial phenomenon that has puzzled astronomers for centuries. It appears as a soft, diffuse glow along the path of the ecliptic, the same plane where the planets travel, visible just after sunset or before dawn. For years, scientists assumed it was simply sunlight reflecting off dust particles scattered throughout the inner solar system, leftovers from comets and asteroid collisions. But recent discoveries have turned that tidy explanation on its head, revealing a mystery that might rewrite our understanding of the solar system's hidden architecture. The conventional story goes like this: over billions of years, asteroids grinding against each other and comets shedding material filled the space between planets with fine dust. Sunlight hits these tiny particles, scattering light back toward Earth in the same way fog reflects car headlights. Observations seem to back this up. Telescopes detected dust trails following comets, and spacecraft like Pioneer 10 and 11 carried instruments that measured interplanetary dust. But then, in 2017, NASA's Juno mission to Jupiter made an unexpected discovery. As the spacecraft hurtled through space, its star tracking cameras were pelted by dust grains far more than predicted, and moving at speeds that didn't match the sluggish orbits of typical asteroid debris. Even stranger, the dust seemed to be coming from the direction of Mars, hinting at an unknown source flinging particles into space at high velocities. This raised a tantalizing question. What if the zodiacal light isn't just ancient dust, some researchers now speculate it could include material from interstellar visitors, tiny particles drifting in from other star systems, mixing with our solar system's debris. Others suggest the glow might be fueled by a still undiscovered population of asteroids orbiting closer to the Sun than Mercury, a region notoriously difficult to observe because of the Sun's glare. These so-called volcanoids, if they exist, could be constantly replenishing the dust cloud through collisions, creating a dynamic, ever-changing contribution to the zodiacal light. But the plot thickens even further. In 2020, the Parker Solar Probe made a startling observation. The dust density near the Sun drops off dramatically, almost as if something, perhaps the Sun's immense heat, is vaporizing particles before they can spread outward. This dust-free zone contradicts older models that assumed dust was evenly distributed, suggesting the zodiacal light sources might be more localized and recent than we thought. Could there be a massive, unseen comet reservoir in the outer solar system, sporadically dumping fresh material into the inner system? Or could solar magnetism be sorting dust by size, creating pockets of varying density that sculpt the light's elusive glow? What makes this enigma so compelling isn't just the scientific detective work, it's the way the zodiacal light bridges the everyday and the extraordinary. This faint glow, visible to the naked eye under the right conditions, connects us to processes spanning the solar system and beyond. Whether it's interstellar dust whispering secrets from other stars or the wreckage of unseen asteroids lurking near the Sun, the zodiacal light is more than a pretty sky phenomenon. It's a cosmic puzzle box waiting for the next generation of missions, like the European Space Agency's Comet Interceptor or NASA's upcoming EMAP probe, to crack it open. And when they do, we might just find that the solar system's dust holds clues to everything from planetary formation to the very journeys of stardust between the stars. Among the countless galaxies swirling through the cosmos, Hoag's object stands apart, not just as another spiral or elliptical, but as a perfect cosmic bullseye. Discovered in 1950 by astronomer Art Hoag, this peculiar galaxy floats 600 million light-years away in the constellation Serpens, defying classification with its mesmerizing symmetry. At its heart lies a golden-yellow core of ancient stars, while a nearly perfect ring of younger, blue stars encircles it like a halo, separated by a vast, dark gap so clean it looks artificial. If most galaxies are cosmic splatter paintings, Hoag's object is a meticulously crafted mandala, challenging everything we know about galactic evolution. The first mystery is its structure. Unlike typical spiral galaxies, where arms branch from a central bar or blend into the core, Hoag's object has no connecting features, just a void between its core and ring so pronounced it could fit an entire second galaxy inside. This isn't just unusual, it's nearly unparalleled. Only a handful of known ring galaxies, like the Cartwheel Galaxy, share this trait, and even those show signs of distortion or collision. Hoag's object, by contrast, appears pristine, its geometry so flawless it seems untouched by the violent mergers that typically reshape galaxies. So how does something like this form? The leading theory for most ring galaxies involves a head-on collision, a smaller galaxy plunging through a larger one, sending shockwaves through the gas and dust that trigger star formation in an expanding ring. But Hoag's object shows no signs of a recent impact, no twisted debris, no trailing stellar streams, no telltale warping in its core. Instead, some astronomers propose a slower, more elegant process, a resonance wave. Imagine dropping a pebble into a still pond, but instead of ripples fading, they freeze into a permanent ring. In galactic terms, gravitational instabilities could have caused the outer disk to contract and expand rhythmically, compressing gas until it ignited into a circle of newborn stars. Yet even this explanation feels incomplete. Why is the ring so perfectly aligned? Why does the core lack the supermassive black hole activity seen in most galaxies? And most baffling of all, what's hiding in that dark gap? Some speculate it's filled with invisible dark matter, its gravity sculpting the ring like an unseen hand. Others wonder if the gap hosts a population of faint, old stars too dim for our telescopes. The James Webb Space Telescope might soon offer clues, peering into the void with infrared eyes capable of spotting hidden stellar fossils. What makes Hoag's object so captivating isn't just its rarity, it's the way it forces us to rethink galactic diversity. For decades, astronomers categorized galaxies into neat bins, spirals, ellipticals, irregulars. Hoag's object defies them all, a cosmic outlier that suggests the universe's creativity knows no bounds. Whether it's the product of a forgotten collision, a delicate dance of resonances, or something entirely unknown, this celestial enigma reminds us that even the most familiar corners of the cosmos can still surprise us. And until we unravel its secrets, it will remain a silent challenge, a perfect ring hanging in the dark, daring us to look closer. Venus, the toxic hellscape of our solar system, hides one of the most bizarre weather systems ever discovered, a swirling, permanent double-eyed vortex spinning above its south pole like a pair of cosmic hurricanes locked in an endless dance. This storm defies all logic. Hurricanes on Earth thrive on warm ocean water and rapid planetary rotation, but Venus has neither. Its surface rotates agonizingly slowly. A single day there lasts longer than its year, and its bone-dry atmosphere should be the last place you'd find a persistent whirlwind. Yet there it is, a monstrous tempest stretching over 2,000 kilometers wide, churning in defiance of every atmospheric model scientists have thrown at it. The discovery came in 2006, when the European Space Agency's Venus Express probe trained its infrared cameras on the planet's polar region. Instead of the expected chaotic turbulence, it captured a stunningly organized structure, two distinct centers of rotation nested within each other, forming a figure-8 pattern that waxes and wanes but never fully dissipates. Think of a hurricane with two eyes, each influencing the other in a delicate balance, except this isn't a fleeting anomaly. It's been raging for at least decades, possibly centuries, an atmospheric perpetual motion machine that shouldn't work but does. What keeps this vortex spinning against all odds? The answer lies in Venus's super-rotating atmosphere, a phenomenon where the planet's upper air currents scream around the globe at 360 kilometers per hour, 60 times faster than the surface below. This creates colossal shear forces, whipping up storms that would dwarf anything on Earth. But the polar vortex adds another layer of mystery. Unlike Earth's polar vortices, which are cold and high altitude, Venus's beast is warm, centered about 65 kilometers above the surface in a layer of sulfuric acid clouds. Some researchers believe the vortex is fed by giant atmospheric waves similar to Earth's jet streams but cranked up to 11. That channel energy toward the poles, creating a self-sustaining feedback loop. Then there's the shape. Double-eyed vortices aren't unheard of. Jupiter's great red spot occasionally sprouts smaller companions, but Venus's version is freakishly stable. Computer simulations suggest the planet's unique conditions might act like a celestial blender, taking incoming winds and folding them into this precise, symmetrical pattern. One theory posits that the vortex's twin cores are trapped in a gravitational tug-of-war with Venus's highland regions, particularly the massive Aphrodite Terra continent, whose towering mountains might sculpt the upper atmosphere like a rock diverting a river. But the real stumper is persistence. Earth's hurricanes die within weeks when they hit land or cold water. Venus has no oceans, no land masses at that altitude, just a searing, acidic haze. So why doesn't the vortex fizzle out? The secret might lie in something called the thermal tide. On Venus, sunlight heats the thick atmosphere so intensely it creates pressure waves that circle the planet, pumping energy into the vortex like a cosmic bellows. It's as if the storm has found a way to parasitize Venus's extreme climate, turning its lethality into a power source. The Venus vortex isn't just a curiosity, it's a masterclass in atmospheric extremes. By studying how this storm cheats death, scientists gain insights into exoplanet weather, especially on tidally locked worlds where one side always faces its star. It's a reminder that nature's playbook is far stranger than we imagine, and that even in the most hostile corners of the cosmos, order can emerge from chaos if you know where to look. For centuries, we've pictured the Milky Way as a relatively serene spiral, its stars tracing orderly orbits around the galactic center. But in 2022, astronomers uncovered something that shattered that calm illusion, a series of colossal ripples warping the entire disk of our galaxy like a stone dropped into a cosmic pond. These aren't gentle undulations, they're titanic waves, some stretching thousands of light years from crest to trough, rolling through the starry plane with enough force to fling entire star clusters into unplanned trajectories. And the most unsettling part, no one knows what caused them. The discovery began with Gaia, the European Space Agency's star mapping powerhouse, which has plotted the positions and motions of over 1 billion Milky Way stars with unprecedented precision. When researchers analyzed this treasure trove of data, they spotted something bizarre: groups of stars oscillating in sync, bobbing up and down through the galactic plane like buoys in a slow-motion tsunami. These waves aren't random noise, they form a coherent pattern, suggesting a single, catastrophic event set them in motion. One leading theory points to a past collision, perhaps with a dwarf galaxy or a massive dark matter clump that plowed through the Milky Way's disk like a bullet through water, leaving these gravitational echoes in its wake. But the timing is a mystery. Some calculations suggest the ripples could be remnants of the Sagittarius dwarf galaxies, repeated collisions with the Milky Way, a tiny but pesky neighbor that's been orbiting and occasionally smashing into our galaxy for billions of years. Others propose an even more dramatic culprit, the long-ago passage of the mysterious Gaia sausage, a hypothesized galaxy that might have merged with the Milky Way 8 to 10 billion years ago, its debris still shaping our galaxy's structure. The problem: neither scenario perfectly matches the wave's scale or current motion, leaving astronomers scrambling for alternative explanations. Could it have been a rogue black hole, a subhalo of invisible dark matter, or something even stranger? What makes these ripples so extraordinary is how much they reveal about the Milky Way's hidden history. Like tree rings recording ancient droughts, these warps encode violent events we never witnessed, collisions and close calls that reshaped our galactic home. By tracking the ripple spread, scientists can essentially rewind time, reconstructing the forces that sculpted the galaxy we see today. Already, they've found that the waves affect more than just stellar motions. They're warping the galaxy's magnetic fields and even redirecting the flow of interstellar gas, the raw material for new stars. Yet the biggest surprise might be how little we still grasp about our own cosmic backyard. For all our star maps and simulations, the Milky Way remains full of surprises, its serene facade masking a turbulent past. These ripples are more than a curiosity. They're a reminder that galaxies aren't static paintings but living, breathing entities, forever shaped by the invisible hands of gravity and time. And as Gaia continues its survey, who knows what other secrets might surface from the depths of our own spiral sea? The Big Bang didn't just create space and time, it forged the universe's first elements, a primordial alchemy that set the stage for everything to come. In those first fiery minutes, protons and neutrons fused into hydrogen and helium, with trace amounts of lithium sprinkled in like cosmic seasoning. The math was precise. Based on the conditions of that explosive birth, scientists calculated exactly how much of each element should have formed. Hydrogen and helium matched predictions beautifully, but lithium, the universe came up short not by a little, but by a jaw-dropping threefold. This isn't just a rounding error, it's a glaring hole in our understanding of cosmic chemistry, one that's had astrophysicists scratching their heads for decades. So where did all the lithium go? The discrepancy exists in two forms. Lithium-7, the heavier isotope, appears at just a third of its predicted levels in ancient stars, the celestial time capsules that preserve the early universe's composition. Even more baffling, lithium-6, the lighter sibling, is virtually absent when models say it should be detectable. This isn't a case of bad measurements. Observatories like the Very Large Telescope have double-checked the numbers to the point of exhaustion. The conclusion is unavoidable. Somewhere between the Big Bang and today, lithium vanished. One leading suspect is stellar physics. When lithium encounters the searing heat of stars, it's fragile. Unlike helium, it breaks apart easily. Old stars, especially those with convective outer layers, might have acted like cosmic blenders, churning lithium down into their cores where temperatures annihilate it. But here's the catch. While this explains some of the loss, simulations show stars shouldn't have destroyed this much. Even accounting for stellar digestion, the numbers still don't add up. Then there's the wild card, primordial black holes. Some theorists suggest these hypothetical relics from the universe's first second could have swallowed lithium-rich gas before it ever formed stars, erasing the element from the cosmic ledger. Others propose exotic physics like undiscovered particles interacting with lithium nuclei in the early universe or variations in the fundamental constants that altered nuclear reaction rates. It's a grab bag of possibilities, each more speculative than the last, but that's the nature of the lithium problem. When conventional explanations fail, you start eyeing the unconventional. What makes this enigma so frustrating and fascinating is how it connects the unimaginably vast to the infinitesimally small. Lithium's absence isn't just a celestial bookkeeping error. It's a potential window into physics beyond the standard model, a hint that the early universe played by rules we haven't yet uncovered. Whether the answer lies in better stellar models, revolutionary cosmology, or something no one's dreamed up yet, the missing lithium remains a quiet but persistent reminder. Even the universe's oldest receipts don't always add up. From rogue planets adrift in the cosmic dark to galaxies shaped like perfect rings, the universe has shown us time and again that reality is far stranger than fiction. We've chased whispers like the wow signal, grappled with invisible giants like dark matter, and stared into voids so vast they defy logic. Yet for every mystery we've scratched the surface of Tabby's star's eerie dimming, Saturn's impossible hexagon, the great attractor's relentless pull. There are countless others waiting in the shadows, each one a reminder of how small our understanding truly is. Think about it. We live in a cosmos where black holes spin spacetime into knots, where entire galaxies are being dragged toward some unseen destination, where the very laws of physics seem to rewrite themselves at the edges of our perception. The Hubble tension alone, that stubborn mismatch in the universe's expansion rate, could upend cosmology as we know it. And what about those bizarre lunar rocks, whispering of a time when the moon had its own magnetic shield? Or the cold spot in the cosmic microwave background, a cosmic bruise that might just be evidence of a parallel universe bumping against ours? These aren't just puzzles, they're doorways to discoveries we can't yet imagine. But here's the beautiful part: every unanswered question is an invitation. The universe isn't taunting us with its secrets, it's daring us to look deeper, to build better telescopes, to dream up wilder theories, and to stay relentlessly curious. Because the next big revelation might be hiding in the flicker of a distant star, the echo of a gravitational wave, or the static of a radio signal we haven't thought to listen for yet. So keep wondering, keep questioning, and most of all, keep looking up, because the cosmos is far from finished surprising us. Who knows, the next galactic enigma might be discovered tomorrow, and you could be the one to help unravel it. Until then, the universe will keep its mysteries close but not